Okay, so we had this series of phosphoric acid losing one hydrogen to form dihydrogen phosphate, losing another hydrogen to form hydrogen phosphate, and then finally losing its last hydrogen to form phosphate ion itself. And if we look at these two species in the middle here, H2PO4-, it can gain a hydrogen or it can lose a hydrogen, which means it can act as a base when it gains a hydrogen and accepts a proton, in other words, or it can act as an acid and donate a proton when it turns into HPO42-. HPO42- also can accept a proton to go this way, or it can donate a proton to go that way. So they are able to be either an acid or a base. And you know, that kind of matches how we label them here. H2PO4 is the weakest base, but it's the middle acid, so clearly it's able to be both. Which it does will depend on the context of who its reaction partner is. And we're not going to give you overly complex problems. It will be obvious whether it's going to act as a base or whether it acts as an acid, because its reaction partner will either be a base or an acid. So if I take H2PO4- and I react it with hydrochloric acid, the hydrochloric acid is going to give it a proton. It will act as a proton acceptor and be a base. If I take H2PO4- and react it with sodium hydroxide, well, the sodium hydroxide is a base. It's going to want to accept a proton, and so H2PO4- will donate its proton and act as an acid. Hopefully that makes sense. These, I should erase this now. I'm going to erase this up here. So these two, which are capable of acting as either an acid or a base, are called amphoteric. Sometimes they're also called amphiprotic. So just like an amphibian can live on both land and water, amphoteric and amphiprotic species can either donate or accept a proton in reaction. Now I've added down here how water itself is a part of a series like this. H3O+ can lose a proton to form water. Water can gain a proton to form H3O+, and so they are a conjugate pair. Water is the conjugate base to the acid of hydronium ion. And then water can lose a proton to form OH-. OH- can gain a proton to form water, so water is the conjugate acid to hydroxide ion. And that means that water itself is a member of the family of amphoteric or amphiprotic chemical species. Water can act as an acid or as a base. Now, remember, this was a middle acid but a strong base. The acid strength and the base strength were different from each other. Well, water is unique because it is equally strong as an acid or a base. We can show the reaction where water reacts with itself. If I have one water acting as an acid and one water acting as a base, so the acid is going to give an H+ to the base, then what will my products be? H3O+ aqueous plus OH- aqueous. So this is the autoionization or autoprotolysis reaction of water, where water acts as an acid and a base, and it produces both H3O+ and OH minus. And if we were to take the equilibrium constant for this reaction, then it would simply be H3O plus OH minus. And this isn't really a Ka or a Kb. It's kind of both a Ka and a Kb together. It's really a unique and special type of a constant. So what we will call it is Kw, or the water autoionization constant. And Kw is equal to 10 to the negative 14th. And that's good to a couple of significant figures. So I guess I should say it's equal to 1.00 times 10 to the negative 14th. A very happy coincidence, because it makes a lot of our math that we're going to be doing later much easier. First of all, this reaction happens all the time. If you have pure water and there's no solute in it, maybe you've distilled it or done reverse osmosis or done whatever you can to get the most pristine, pure sample of water that you can find, it's still not going to be pure water, because we can't prevent water from reacting with itself in this way and producing hydronium and hydroxide. Every drop of water on the earth has some hydronium and some hydroxide. And the amounts must obey the equilibrium constant here. And so H3O plus concentration times OH minus concentration is going to equal 10 to the negative 14th. As one of them goes up in concentration, the other one must go down in order to maintain this equilibrium expression. Now, if H3O plus and OH minus are equal to each other, that's what we define as a neutral solution. It's not acidic or basic, it's neutral. If they're equal to each other, then their concentration will be the square root of Kw, and this is going to be 1.00 times 10 to the negative 7th. And at this point, I want to go back to a figure we were looking at earlier today. Hold on, there it is. Okay, so this is back to figure 10.1, and you'll notice here that if you look at the concentrations of H3O plus and OH minus, then their product will always equal 10 to the negative 14th. If we look at here by milk of magnesia, the H3O plus concentration is 10 to the negative 10th. The OH minus is 10 to the negative 4th, and multiply those together, you get 10 to the negative 14th. If you come down here to lemon juice, H3O plus is 10 to the negative 2nd, OH minus is 10 to the negative 12th. Multiply those together and you get 10 to the negative 14th. And then here at pure water, right in the middle, perfectly neutral, they are both 10 to the negative 7th. So Kw is going to be very important in governing how H3O plus and OH minus are constrained to have their product both equal to 10 to the negative 14th, which is really important to how acids and bases behave. So we'll go into a lot more of the math. So we've given you Ka values, we've given you Kb values, and now Kw. These are the tools that we're going to use to do more quantitative work with acids and bases moving forward. We'll do that next week.